Hello everyone, my name is Rupesh Verman. Today I will be presenting my research work titled as a combined theoretical experimental numerical approach to characterization and modeling of rock fracture and rock burst. I did finish this research work as a part of my PhD thesis at the University of Adelaide under the supervision of Professor Jiang, Professor Murad, and Professor Abbas. This lecture will be a part of a series of lectures on PhD thesis related to deep mining geomechanics for ISRM Commission on deep mining. About my introduction, I am a civil engineering graduate. Thereafter, I did my master's in geotechnical engineering and doctor's or PhD in rock mechanics in 2020. After my PhD, I did work as postdoc researcher for 2 years, and thereafter operational geotechnical engineer in underground mine, and also geotechnical engineering consultant in number of consultancies. Currently, I am working as a lead geotechnical engineer in one of the deepest mine in Australia, that is CSA mine, located in Cobar. I have divided the key content of this lecture into 8 different sections, starting from introduction and background of my research, followed by research outline, and three main component of my work, that is experimental, numerical, and theoretical, followed by conclusions and applications of the work we conducted and corresponding publications. Rock burst is a broad term often used to indicate a violent failure of rock in deep underground mining conditions. When I say deep underground mining conditions, I mean high in situ stress scenarios. As we go deeper, the in situ virgin stress keeps on increasing, and when we do underground mining, when we excavate the underground in such a situation, the stress around the opening further intensifies, which often, especially in hard and brittle rocks, result in violent failure of rock. One example is shown in video where the bursting event has occurred and it has lifted the entire 4-ton vehicle. This video presents another example of bursting, that is rock burst. It will occur on the right hand side floor of this drive. You can see. Yep. As you can see that these two miners did narrowly escape this event, right? Which is not very common. Often the bursting, it occurs at relatively higher magnitude, which results in severe consequences that include loss of lives, delay in project, economic loss, loss of time, and sometimes it also triggers seismic events, which of course can be fatal. As I mentioned earlier, rock burst is a broad term. There are different classifications of rock burst available in the literature. One of these are pillar burst, strain burst, and fault slip burst. This work is focused on strain burst, that is bursting of rock around underground opening in deep underground mining conditions because of high stored elastic strain energy. When we go deeper, right, the rock mass is highly stressed, and when we excavate, the strain energy stored in the rock mass around the opening sometimes exceeds its requirement to cause failure, and that excess strain energy releases when we provide a free face in the form of excavation, and that release of excess strain energy is often violent in the form of bursting, and that's what we call strain burst. You can see 3 examples of strain burst where mesh bulking and failure in the back and the side walls has occurred because of this violent event. Yeah, strain burst is a complex problem. If we look at the underground scenarios, each scenario is different. So explicit evaluation of bursting can be very complicated and it may not be practical. However, we need to understand that if the rock in the rock mass around the underground opening has the potential to burst, strain burst may likely occur. However, if the rock lacks the potential to burst, then in situ conditions, it is very unlikely the strain burst will occur. So, the focus of this research was to develop an energy based framework to quantify the burst potential of rock. So, to evaluate this, there are four main factors to be considered. The one is material property, which in principle controls the mechanical response of rock in any loading unloading conditions. Second factor is in situ stress conditions, that includes virgin in situ stress and redistributed in situ stress after excavation. That indicates change in the boundary conditions. The last aspect is the geometrical aspect, that means the specimen or the size of the rock around the opening. That in principle is controlled by in situ discontinuities in the form of faults and fractures. Now, to start with, the material properties. There are three main categories of material properties that's required for the estimation of burst potential. The first one is strength, that includes strength of rock under compression and under tension. For compression, we have standard uniaxial compression strength test. Uh, their lateral control is also available to capture the true post-peak behavior under compression. In terms of tension, we have indirect tensile strength test. That's called Brazilian disc test. Now, the applicability or the reliability of its tensile strength estimation is under debate for very long because it depends on the crack initiation point. In the literature, it's been established that if the crack initiates at the center of the disc, then the corresponding result for tensile strength estimation is reliable, else it is not. So that was one thing we need to be focus on in this research. The other properties are elastic properties, include elastic modulus of rock and Poisson's ratio, and energy dissipation characteristics of rock, that include fracture energy in shear band when the rock is subjected to compression. This can be evaluated from uniaxial compression strength test or triaxial test. And the fracture energy in tension, which is very difficult to obtain in this current indirect tensile strength test, because the current Brazilian disc test or indirect tensile strength test lacks the ability to capture true post peak behavior. If we compress the disc specimen, even with the quasi static loading conditions, after peak the specimen cracks uncontrollably and couldn't capture the true post peak behavior. So that lead or motivated us to develop a new experimental approach named OSIBIT. We will be discussing about that more in our further slides. The other factor is in situ stress conditions, followed by changes in boundary conditions. Now, when we excavate, obviously, we provide a free face to the rock around the excavation to dilate. That change in boundary conditions enable rock to release its excess strain energy, and the amount of excess strain energy governs the magnitude of bursting, which needs to be evaluated while calculating the burst potential of rock. And at last, geometrical aspect. There are two categories for that. One is aspect ratio and second is specimen size. When we say aspect ratio, that means if we keep the width and breadth of the specimen constant and keep increasing the height, that means we are changing the aspect ratio of the specimen. And with that change in the aspect ratio of the specimen, how the burst potential of rock is varying, that needs to be considered. And the specimen size as well. That means as we keep increasing the size of the specimen, what effect we can get on the burst potential of rock. So these factors has to be taken when we calculate the burst potential of rock, because in underground in situ scenarios, right, the size of rock is beyond our control. It is governed by in situ discontinuities, which is very difficult to capture for each and every cut in underground mining scenarios, right, when we take cuts in drives and when we fire stopes. So yeah, now to address this problem, what we did in this research is we systematically collaborated three approaches: experimental, numerical, and theoretical, because we understand that not single approach is sufficient enough to address this complicated problem. Now, from experimental approach, the intent was to get the required material property, that is strength, elastic, and fracture properties. Now, as I mentioned earlier, the fracture properties intention was difficult to obtain from the conventional approaches, and that motivated us to develop a new experimental approach called OSIBIT, that is Adelaide University Snapback and Direct Tensile Strength Test. Now, these experiments enabled us to obtain required material properties, including strength, elastic, and fracture. And the OSIBIT experimentation also provided a preliminary indication of the burst potential of rock that later verified from developed theoretical and numerical approaches. In terms of numerical approaches, we adopted a hybrid 3-deck Itasca framework where the tetrahedral block is zoned to ensure that they are deformable. Now these deformable tetrahedral blocks are continuum frame, and these tetrahedral blocks interact with each other via contact. Now the behavior of these contact is controlled by contact model. That means this contact model plays an important role in capturing the fracture in the given rock specimen. Now, when we evaluated the situation of the contact models available in 3-deck Itasca, we understood that those models were relatively basic, and that motivated us to develop a new cohesive contact model and implement that in 3-deck Itasca. Once the developed cohesive contact model was verified and validated, we implemented in 3-deck, and that provided us a numerical modeling framework to perform burst experiments. And at last, in terms of theoretical approach, the intent was to develop a energy based strain burst criteria or energy based framework to estimate and or quantify the burst potential of rock. Now once that framework, that analytical framework was developed, its applicability was verified using numerical burst experiments, and once it's verified, it's good to go, it's good to use for further applications. Now to provide further details, we will go through these individual approaches one by one, starting with experimental approach. As I mentioned earlier, the aim of experimental approach was to estimate the required material properties including strength, elastic, and fracture. For that purpose, we started with two conventional approaches named uniaxial compression strength test and Brazilian disc test. The UCS or uniaxial compression strength test enabled us to calculate UCS strength and elastic properties including elastic modulus and Poisson's ratio. When we started doing Brazilian disc test, we realized there are two key issues associated with this experimentation. The first one is its reliability. In the literature, we found that the reliability of these results heavily depend on the crack initiation point when the disk specimen is compressed diametrically. And the second issue we found is the uncontrolled cracking of the disk specimen, which is the result of local scale uncontrolled dynamics, which has not been addressed in the available literature efficiently. And these issues motivated us to develop a new experimentation named OSIBIT, stands for Adelaide University Snapback Indirect Tensile Strength Test. OSIBIT not only enabled us to calculate the fracture property of rock, but also the effect of specimen size on its mechanical behavior and variation in material property on the post-peak behavior of rock as well. It also enabled us to get a preliminary estimation of the burst potential of rock. Now, Brazilian disc test. You can see it's a simple experiment. In this experiment, we take a disc shape specimen and we compress it diametrically and record load versus displacement response. And we capture the peak load at which the specimen cracks. Now that peak load P is linked with the tensile strength of the material. Simple experiment and easy to perform. Now the issue was, first, the reliability of the tensile strength test. In the literature, it was stabilized that if the crack initiates at the center of the disc specimen, then the corresponding peak load will provide a reliable estimation of tensile strength. However, in the literature we have seen, and in the laboratory experiments also we have seen, that often crack does not initiate at the center of the disc. Instead it initiates at the loading ends because of high localized compression. Now, in those scenarios where the crack is not initiating at the center of the disc specimen, the reliability of tensile strength estimation can be debated. The second aspect is its uncontrolled dynamics. We can see that this experiment can efficiently capture the class 1 behavior of rock. However, it cannot capture the class 2 behavior, which is more common in hard and brittle rocks. In those cases, as we reaches to the peak load P, the specimen cracks uncontrollably and the load drops immediately to its residual strength. And there was no way it could capture the class 2 behavior, which indicates the true mechanical post-peak behavior of the given rock type or the brittle material. As mentioned earlier, the first issue was the correct tensile strength estimation. So we started with using advanced instrumentation. We thought with high speed camera, that is digital image correlation technique, we can capture the local scale behavior in quantitative terms and link it with material property like tensile strength estimation. However, we realized that the disc specimen cracks in a fraction of a time second window, which is very quick, and we can see the cracking pattern as well, which clearly shows that the crack happens and there after crack there has been a release of excess strain energy, which might have resulted in these secondary cracks. Now, with the high speed camera, we tried different frames per second with different image capturing speed. We started with 5 frames per second and we extended it to 150 frames per second. However,
with all these variations in frame per second, we realize that the local scale dynamic is so dominant that it couldn't allow us to quantify or to capture the local scale behavior in quantitative terms to link it with material property. And that made us realize that snapback is not about high speed instrumentation, but it is about the local scale dynamics. If we could control this local scale dynamics associated with disk cracking, we could enable an efficient application of digital image correlation or high speed instrumentation. Else we could else yeah, these approaches could be limited to strain contours as well without any quantitative assessment. Thereafter, we again went back to literature to evaluate whether there has been done anything regarding this issue of uncontrolled cracking. And we realized lots of work has been done. However, most of these work in literature around indirect tensile strength test was focused on ensuring the crack initiation at center of the disk. The number of changes recommended in literature to change the loading angle to ensure that the crack initiates at the disk specimen, at the center of the disk specimen. These approaches were successful up to a certain extent, but their application on various brittle materials can be debated. And at the same time, we realize that the issue of uncontrolled cracking of disk specimen has not been addressed efficiently in the available literature. And that motivated us to develop a new experimental approach named OSIBIT, that stands for Adelaide University Snapback Indirect Tensile Strength Test. Uh, the OSIBIT experimentation setup is relatively simple or straightforward, we can say. In this experimentation, we use lateral LVDT to capture the lateral deformation of the disk specimen, and that information governs the vertical diametrical loading rate of the disk specimen. So what we do in this setup is we ensure that the disk specimen undergoes constant or consistent lateral deformation throughout the experiment. That means if the lateral deformation of the disk specimen increases, the OSIBIT experimentation, which uses servo control, tends to reduce the loading rate to ensure that the lateral deformation rate further reduces to our predefined level. And if the lateral deformation rate reduces below our predefined level, the vertical diametrical loading rate increases accordingly. By doing that, we were successful in prolonging the instant cracking of the disk specimen. You can see from these two figures, from these two disk specimen cracking videos, in conventional approach, the disk was cracking in a fraction of a second. Now the same cracking process has been prolonged to several hours in OSIBIT experimentation. The acoustic emission energy response indicate that the whole cracking process is a valid cracking process. It's not machine's mechanical unloading. You can see there has been a consistent release of acoustic energy indicating continuous damage of the disk cracking under the OSIBIT experimentation post-peak response. Now, the immediate benefit of this controlled cracking can be seen from figure A, that is load versus displacement response. In conventional approach, where the disk crack immediately after reaching its peak load P, and the cracking pattern also includes the secondary cracks indicating the release of excess strain energy. The same disk specimen in controlled oscillate experimentation uh, can produce true post-peak behavior with snapback response. And the crack can also be seen that there is no sign of secondary crack. That means the specimen has consumed the amount of strain energy that is required for vertical diametrical crack, and the excess strain energy has been successfully removed to enable the snapback response and to capture the true post peak behavior of the disk specimen. In terms of time frame window, we can see that the disk specimen, which was cracking in a fraction of a second, now the post peak response, the post peak cracking behavior has been prolonged to several hours. So yes, we were successful in performing oscillate experimentation on Hawkesbury sandstone rock type. Now we want to ensure that this experimentation can be applied to other brittle materials as well. So we extended its application to harder and brittle rocks including Iranian granite and bluestone. We also extended its application to concrete. Now from the normalized load versus displacement response, we can see that the concrete on one hand undergoes or performs class 1 response in terms of its post peak behavior, whereas the brittle materials like rock demonstrate class 2 behavior. Now these class 1 and class 2 behavior were both successfully captured by oscillate experimentation, which was not possible earlier in the conventional approach. Now, yes, oscillate can capture post-peak behavior, true post-peak behavior of disk specimen under diametrical cracking. But what are the other advantages? So if we list all the benefits of oscillate applications, we can start with tensile strength of estimation, which is, of course, it's already there. Apart from that, we can calculate the fracture property of rock. In oscillate experimentation, we can capture the snapback response or true mechanical post-peak behavior of disk specimen, which wasn't possible in the conventional approach. Now, because of this snapback response, now we can calculate the excess strain energy and the strain energy required to cause or to create vertical diametrical crack. With that, now we can calculate the fracture energy and fracture toughness using the same oscillate experimentation. In addition to this, we can also assess size effect. There are two types of size effect. One is statistical size effect and the second one is energetic size effect. Statistical size effect is like as we increase the size of the disk specimen, we end up getting lower tensile strength. This is because as we increase the specimen size, we can expect the increase in the inherent defects, and that inherent defects because of increased specimen size result in lower estimation of tensile strength, relatively lower estimation of tensile strength. Now this statistical size effect can be evaluated from conventional approach and from oscillate experimentation as well. However, the energetic size effect cannot be captured or assessed via the conventional approach. However, thanks to oscillate, we can now analyze that as well. The energetic size effect is like the effect of specimen size on the post-peak snapback behavior of the disk specimen. So as we keep increasing the size of the disk specimen, we expect relatively higher magnitude of snapback response, because as we increase the disk specimen size, the volume of the disk specimen, increase will result in increase in the strain energy stored in the disk specimen. At the same time, the fracture energy requirement also increases, but that increase is in correspond to the fracture surface. Now the difference between these two energy requirement, that is strain energy stored inside the disk specimen, which increases with volume, and the strain energy required to cause fracture in the disk specimen, that is diametrical crack, which increases with crack surface. That difference result in the variation in the post-peak snapback response that correspond to the energetic size effect, which thanks to Osobit now we can capture. In addition to this, we can also capture the effect of material change on the post-peak behavior, as we have seen in the previous slide that the as the material become harder and brittle, we observed higher magnitude of snapback, whereas if the material become less brittle like concrete, we observe even class 1 behavior. So both class 1 and class 2 behavior can be captured by Osobit experimentation, which could be the result of variation in material effect. Addition to this, as I mentioned earlier, Osobit enabled efficient application of advanced instrumentation, including digital image correlation technique and acoustic emission technique. And these efficient application of advanced instrumentation enabled us to link the local scale behavior with the material properties in quantitative terms, and that also enable us to get a preliminary estimation of burst potential of rock and the material brittleness. With this successful application of Osobit experimentation, the next stage was to ensure that this experimentation can be applied to a variety of brittle materials. So as I mentioned earlier, we started with Hawkesbury sandstone, and then we extended its application to Iranian granite, which is much stronger and brittle material as compared to sandstone. And then we further extended its application to bluestone, which is even stronger and brittle as compared to the earlier two rock types. And we further extended its application to Australian granite as well. On the other side of the spectrum, we extended its application to concrete, which presented class 1 response as compared to the brittle rocks like bluestone, Australian granite, and Iranian granite. We extended its application to coal as well, and 3D printed cement paste as well, with different bedding orientation. Now as you can see that the Osobit can be applied to a variety of brittle materials, ensuring its effective and larger application across the varied spectrum of brittle materials. After experimental, the second approach we adopted in this research is numerical modeling approach. For this approach, we used hybrid numerical modeling framework provided by Tasca 3DEC. The intent of this framework, this approach, is to develop a numerical modeling, 3D numerical modeling space where we can perform numerical strain burst experiments outside the calibrated dataset. For that purpose, we developed a new cohesive contact model, and we implemented that model in 3DEC Tasca. The intent here was to capture the realistic or reliable cracking behavior or specimen fracture behavior under the given loading conditions. And we used this numerical modeling framework to calibrate using UCS and Brazilian disk test, and later used to perform burst experiments. Now to start with the fundamentals. Now we can see the rock specimen, right? So the rock specimen is basically a combination of grain aggregates, and these grain aggregates interact with each other via contact forces because of intergranular cementitious bonding. Now when we subject this rock specimen to any given loading condition, for example uniaxial compression, this specimen cracks because of the loss of intergranular cementitious forces, and the crack in majority of cases is due to the loss of these contacts, not because of grain crushing. Now to mimic that fracture process numerically, in 3-deck we use 3D tetrahedral blocks. Now these 3D tetrahedral blocks were made deformable via zones, and these 3D tetrahedral blocks interact with each other via contact model. Now these contact model play an important role in capturing the intergranular cementitious forces. Now to capture that intergranular interaction in a realistic manner, we need a reliable contact model, and at that time we realized that the available contact model in 3-deck Itasca were quite basic, and they were not quite accurate in terms of capturing the post peak behavior in tension and shear and mixed mode loading condition and so on. That motivated us to develop our own cohesive contact model and implement that in 3-deck Itasca. Now in terms of cohesive contact model, the details can be seen in the publication as shown below in the slide. The contact model under tension in post-peak behavior results in gradual degradation of strength, unlike immediate drop as shown in various available models in 3-deck and in other published literature as well. And same goes under shear as well. The post peak behavior, the post peak strength of the contact, it degrades gradually, and that degradation is in correspond to the damage, and the magnitude of damage not only controls that degradation but also degrade the elastic response as well. So you can see that before peak we have certain stiffness, and that stiffness reduces with damage in post peak response, which truly captures which captured by this contact model in true sense. This cohesive contact model also proposes a unified yield surface, and that yield surface evolved with damage. As the magnitude of damage increases, the yield surface shrinks, and eventually when damage reaches to its maximum value, it shrinks down to the residual yield surface to capture the cracking process, the post peak degradation of contact strength. Same goes for plastic potential, and the parameter this cohesive contact model uses is cohesion, tensile strength, friction, and dilation. Now cohesion and tensile strength can be obtained from experiments directly. Other properties need a bit of calibration. The damage is indicated by D, which increases with plastic potential with plastic deformation of the contact. Once the contact model was developed, it was verified using analytical solutions and numerical solutions, and thereafter it was validated using a mixed mode loading experimental case available in the literature. And once it's validated, it was further implemented in Theoretical-Experimental. For that purpose, we used user-defined option in the Theoretical-Experimental and fish coding along with C++ programming to write that cohesive contact model code and implement it in 3DEC. Once implemented, the cohesive contact model was further validated using the experiments of mixed mode loading available in the literature. Once validated, this cohesive contact model, which was implemented in Theoretical-Experimental, is now calibrated to the given rock type. In our case, that is bluestone. For this calibration process, we used two experiments. One is uniaxial compression strength test, and second one is Brazilian disc test, that is indirect tensile strength test. The result of uniaxial compression strength simulation is shown in this given slide, which shows a really good correlation with the numerical output with the experimentation observation. Now, these correlation were found to be good not only at the sample scale but also at the local scale damage process, the details of which can be seen in the publication shown below in the slide. The next set of experimentation simulation in this process of calibration was Brazilian disc test. We can see that the load versus displacement response or strain response here from these two sources, that is, one is from numerical model and the other one is from experimentation, are pretty much well aligned. And at stage 1 we can see that the local scale damage, it started from the loading end, and that corresponds well in both numerical and experimentation. From experimentation we obtain this strain contours using digital image correlation technique, whereas from numerical we got the strain contours straight away. At stage B, when the specimen cracks, the disc specimen cracks like instantly, in a fraction of a second, and that cracking pattern of numerical modeling assessment also aligns well with the experimental observations, as you can see in the slide below. And in the stage 3 post-peak behavior, we can see a significant amount of secondary cracks at the loading ends, which also correlates well from numerical output and are in correspond with the experimental observations. The video shows the damage evolution across the specimen diametrical axis in this conventional approach. Once the numerical modeling framework is developed and calibrated to the given rock type, that is bluestone in our case, the next approach is the theoretical one that we used in this research. The main aim of the theoretical approach is to develop a energy-based framework which can link key material properties including strength, elasticity and fracture with the burst potential of rock. This energy-based framework that we have developed in the presented research proposes a burst envelope concept which can quantify the burst potential of rock, and we used the developed numerical modeling framework to verify the theoretical predictions. As mentioned earlier, the burst potential of rock depends on four key important factors that include material properties, in situ stress conditions, geometrical aspect, and boundary condition changes. Now, as you can see that in this given example, when we excavate in underground scenario, the excavation provides a free face. Now, in the virgin stress state, if the rock is highly stressed and somehow storing more energy than its fracture requirement, and in the virgin stress state, it is in a confined form. Now, when we excavate, we provide a free face. We remove the confinement, and because of this confinement removal, the rock, which is highly stressed and storing significant amount of strain energy, gets a free face to dilate, and that dilation can be violent, and the magnitude of dynamics or violent cracking because of that free face dilation depends on the amount of excess strain energy stored inside the specimen, and that in principle governs the magnitude of strain burst. This in principle forms the basis of our size dependent energy based strain burst criteria or strain burst framework. There are two important components of this criteria. The one is elastic stored strain energy before bursting, and the second one is dissipation capacity. The elastic stored strain energy depends on the material type and its volume or the size of the specimen, whereas the dissipation capacity again depends on the material property and the fracture surface. Now, when it's gonna burst, right? So that depends on the potential of the burst, which in our framework is indicated by this letter P. That's the ratio between elastic strain energy stored inside the specimen to the dissipation capacity. How this strain burst framework works? This strain burst framework provides a burst envelope. This is a 3D surface in three-dimensional principal stress space. Now, for the given rock under the given in situ conditions, it will undergo bursting if the resultant stress state is located outside this burst envelope and it crosses the yield surface. If it is outside the burst envelope but still not crossing the yield surface, that means that specimen is still confined and it's not going to fail. If it is not going to fail, it's not going to burst as well. However, if it is outside the burst envelope and crosses the yield surface, it will burst. The magnitude of bursting will depend on the distance of this resultant stress state from the burst envelope. Higher the distance, higher magnitude of bursting will be encountered. At the same time, if the resultant stress state is inside the burst envelope and crosses the yield surface, the specimen will undergo failure but not bursting. And if the resultant stress state is inside the burst envelope and inside the yield surface, there won't be any failure and of course no bursting. For example, in stress path 1, the resultant stress state, you can see that, is outside the burst envelope and it has also crossed the yield surface. That means after excavation, the bursting will occur in that given specimen where the stress state is outside the envelope and the yield surface. In case of stress path 2, earlier the stress state was outside the burst envelope. However, after excavation, the stress state comes inside the burst envelope and it is not crossing the yield surface as well. So that means there won't be any failure and of course no bursting. In stress path 3, the resultant stress state is inside the burst envelope and it is inside the yield surface as well. So yep, there will not be any failure and of course no bursting. In stress path 4, the resultant stress state, the stress state before the excavation and the resultant stress state both are inside the burst envelope. However, the resultant stress state is crossing the yield surface. So that means in this case, the specimen will undergo failure but not bursting. So this is the concept of the entire burst envelope and how it predicts whether the bursting will occur in the given specimen under the given in situ condition, yes or no, and what will be the magnitude of that bursting. Now, to verify our developed numerical modeling framework, our developed analytical energy based framework, we used numerical burst experiments. For example, we have taken 3 stress paths. So this slide presents an example of stress path 1 where we unload at sigma 1 180 MPa, and as per our theoretical prediction, the strain burst will occur in that scenario because the resultant stress state, as you can see in figure A, is outside the burst envelope and it is also crossing the yield surface. Now, to verify this, we used numerical true triaxial experiment. In that experiment, we have considered a test specimen of the same dimension, and we use platens on all 6 directions. The platen on bottom is fixed and platen on other 2 direction in sigma 2 and sigma 3 direction are also fixed. The other platen on all 3 directions are used to apply polyaxial stress state conditions. In case 1, we first increased all these stresses sigma 1, sigma 2, sigma 3 to this stress state, that is sigma 1 is equal to 30 MPa, sigma 2 60 and sigma 3 80 MPa. And thereafter we kept sigma 2 and sigma 2 and sigma 3 constant and increased sigma 1 to 180 MPa. And after that we removed the platen on sigma 3 direction, so that is kind of mimicking the unloading across the excavation phase. And after that we will evaluate whether the bursting will happen or not. As per theory, a bursting should occur. Now this is what numerical experiment shows. You can see that we reached and unloading, yep, and the bursting occurs. So that verifies our theoretical prediction. We did the same thing with other 2 stress paths as well, and our theoretical prediction was well aligned with our numerical experimentation, numerical burst experiments. That indicates that that verifies the applicability of our strain burst energy based criteria. Now this strain burst criteria also captures the specimen size effect. The specimen size effect has 2 factors. The one is aspect ratio, the second one is specimen size. Now this plot here demonstrates the impact of specimen aspect ratio changes on its burst potential or burst index. As you can see that we have kept width and breadth constant and kept increasing the height of the specimen. With the increase in the height of the specimen, the burst potential of the rock increases up to a certain extent, and after that it stopped further increase with increase in aspect ratio. That is because after certain height the crack across the specimen, the diametrical cracking pattern across the specimen remain almost constant. So that means there's almost nothing, no further increase in the burst index. And that also aligns well with the observations available in the literature. The details can be found in the published article as shown below. The other aspect of size effect is specimen size. As we keep increasing the specimen size, the burst index, the burst potential of rock keep increasing. And by that way, we end up developing a energy-based framework to quantify the burst potential of rock. As we can see that all three components, that is theoretical, experimental and numerical approaches, were very important to develop this energy based strain burst criteria, and this lead to the conclusions of this present study. The graphical representation of key conclusions from this study are as follow. In this study, we systematically collaborated three approaches, that is experimental, numerical and theoretical approaches. The interlink between these approaches were eminent to develop this strain burst criteria, energy based strain burst criteria. The role of experimental approach was to provide the required input parameters for numerical modeling development framework and as an input for theoretical energy based framework application. To do that, we performed two simple experiments, UCS and Brazilian disk test, and we did detailed analysis of the applicability of Brazilian disk test. And after the assessment, we end up developing a new experimental approach patented in Australia named OSIBIT, that is Adelaide University Snapback Indirect Tensile Strength Test. OSIBIT enabled us to obtain not only the fracture properties of rock along with tensile strength, but also the impact of specimen size on its post-peak behavior, efficient application of advanced instrumentation including DIC and acoustic emission, and it also provided a preliminary indication of rocks potential to store and dissipate strain energy, which could control its burst potential in situ underground conditions. Now, the numerical modeling approach. For numerical modeling approach, we utilized hybrid Itasca, 3-deck Itasca numerical modeling framework, where we used deformable tetrahedral blocks interacting via contact model. The blocks indicate or captures the behavior of grain aggregates. The intergranular contact forces because of cementitious bonding is being captured by the contact model. For this purpose, we developed a new cohesive contact model so that we can capture the cracking process in a realistic manner. The cohesive contact model was developed, it was verified using numerical and analytical approaches, and then validated using available data in the literature. Thereafter, it's been implemented in 3-deck Itasca using C++ subroutine and fish coding, and then it was further validated using the data available in the literature. Once the cohesive contact model is implemented in 3-deck Itasca, then it was calibrated using UCS and Brazilian disk test. And once the calibration is done, we end up developing a numerical modeling framework where we can perform a burst experiment numerically that would help us in developing or verifying our theoretical energy based framework. In parallel to the experimental and numerical approaches, we developed a theoretical energy based strain burst criteria. Now, this criteria proposes the concept of burst envelope, which is a 3D surface in three-dimensional principal stress space. Now, this burst envelope, it links the key material properties including strength, elastic and fracture properties of rock, which in principle governs and controls its burst tendency, and link these material properties with in situ stress conditions and boundary changes, and it also takes specimen size effect into account. Now we already have described the functioning of this burst envelope. The resultant stress state post excavation with respect to this burst envelope along with the yield surface governs the potential and the magnitude of bursting. If the resultant stress state is outside the burst envelope and it crosses the yield surface, yes, the strain burst is likely to occur, and the magnitude of strain burst will be dependent on the distance of this resultant stress from this burst surface. That means, which in principle indicates the excess strain energy. That means higher the amount of excess strain energy the rock has, more violent the rock will fail in dynamic manner, that's bursting. Now we used input from experimental approaches and predicted the burst potential for bluestone rock for three different stress paths, and then we verified our theoretical prediction using numerical strain burst experiments. The results from numerical strain burst experiments were in line with our theoretical predictions, which verify the application or the applicability of a burst prediction, burst potential estimation using this theoretical energy based framework. And that leads to the main conclusion of this research, which is to link the material property, specimen size effect, and in situ stress conditions to estimate the burst potential of rock. Obviously, this burst potential of rock will vary depending on the size of the specimen or size of the rock around the opening. Bigger the rock, bigger and stronger the rock, higher its capability to store strain energy in confined manner, and that will indicate it may likely have higher energy access to its fracture requirement. That means after excavation, when a free face is provided, it will release a higher amount of excess strain energy to dilate along the free face, causing bursting. And that leads to the conclusion of my presentation. The key output of my PhD research, that is energy-based framework to quantify the burst potential of rock. Now, in further few slides, I will try to demonstrate its potential applications and in situ ground conditions and future scope. Yeah, this slide presents the application of the developed strain burst energy based framework in one of the underground mine operations as a case study, which is Golden Grove operation located in Western Australia. The details of the underground mine locations at 1300 meter depth, along with rock type and in situ stress conditions, were already published in one of the conferences. And these application of strain burst criteria in this underground scenario will be presented in upcoming conference that is RISEM 11 in Sweden this year, August. Now we can see that there are four major rock type: dacite, rhyolite, dolerite, and host rock. And the in situ virgin stress state is also presented. Now what we did, we applied a strain burst assessment, and that's the result we got. We can see that there are two scenarios. The first one is virgin in situ stress state,
and the second one is resultant stress state after the excavation, after the underground excavation in the form of drive cuts or stope firing. Now, if you see, for virgin in situ stress state, all four rock type do not demonstrate potential to undergo strain burst. Whereas when we excavate, the resultant stress state around the opening changes, and because of that, we can see the potential of host rock to undergo strain burst with the magnitude of 1.9. If this burst index is higher than 1, that means it has a potential to burst. Now, only the host rock has the potential to undergo strain burst. Apart from that, the other rock type do not have the potential to burst. In terms of stress state, both resultant and virgin in situ stress state are all inside the burst envelope of each rock type. That means they will less likely be chances for these rock type to undergo strain burst. Now, what happened in underground scenarios? So this is our prediction. Now, in underground scenario, as per the published paper, the failure of rock mass has been recorded mostly in host rock, not in other rock units. Now, we are saying failure. We need high in situ observations and recording of these failure types and their characteristics to identify whether these are bursting events or conventional failure events. Because the strain burst magnitude, even from the theoretical estimation, is not very high. It's just 1.9. That means even if this bursting might happen, it will be difficult to characterize or to differentiate that bursting from conventional failure. If the magnitude of burst potential is much higher, for example 7, 8, something like that, which could create a clear seismic event in the form of bursting, then it can be clearly identified. But when the bursting happens at very low magnitude, it becomes practically difficult to identify, to differentiate it from the conventional failure. And this might be the case in the underground scenarios where the failure has recorded in the host rock, but there were no comments made about the characteristics of these failures. So these observations are in line with our theoretical predictions. Yes, we agree we need more data, more underground scenarios to to justify, to clearly state whether it's a bursting or it's a conventional failure, on which we are currently working. Yep, we are also collaborating with other underground mine sites where strain burst events has been recorded to get those data and permission to publish the data in collaboration with our developed strain burst criteria. Now, apart from that, this developed energy framework can also be used to assist in designing underground support in underground scenarios where dynamic failure of rock is expected in the form of strain burst or rock burst. Because as you can see that this burst framework can help in evaluating the burst phenomena and the possibility of that phenomena in given underground mining conditions. In addition to that, it can also help us in evaluating the load requirement, especially the dynamic load requirement based on the strain energy storage and releasing characteristics of rock around the opening. And it can be directly used to quantify the burst potential of rock and the factors which can impact the strain burst tendency in the given underground scenarios. And as mentioned earlier, it can help us in deriving the dynamic load demand, and based on that the ground support capacity, whether it's sufficient or not. If it is not, then what sort of ground support that can be used. So it can pretty much help in assisting
in the design of underground support for dynamic loading condition. These are the list of key publications which came from the presented research work. Yeah, finally, I'm happy to present this slide. This is 15th ISRM International Congress on Rock Mechanics 2023, and that's me receiving Rosha Medal Proxim Associate Award for this work that I presented in this lecture. Yeah, we were very happy and glad that our work that we conducted was recognized globally and awarded for Rosha Medal Proxim Associate. Yeah, the intent was to make a contribution, a meaningful contribution to rock mechanics and underground mining society, and we always try to improve and learn. And finally, thank you for your patience and interest. If you have any question, query, or any comments, or you want to discuss anything about this work or strain burst, I would be very keen. Please contact me via LinkedIn or my personal email ID as mentioned here. Yep. Thank you guys. Thank you very much. Cheers. Bye.